Hey there, 30-3s. Here we go with another lesson in our linear relations. So first couple lessons was all about practicing our graphing and calculating slopes. We're going to start looking this lesson about how slope and our graphs give important information. There's two different types of things we're going to look at today. We're going to look at direct variation, and then in this video also we're going to talk about partial variation. Similar with a small twist. What direct variation is anytime we have a graph, if our graph starts down at the vertex, that 0, 0 point, and then goes up in whatever kind of a line with it, whatever slope, but if we go through the vertex, that's direct variation. So let's go back to page 3 and 4. Go back to page 3 and 4 and let's identify on page 3 and 4 which ones are direct variation graphs, and let's calculate the slope of each line. So when we go back, we're going to do those things. So I have the pages now for my direct variation and some partial variation. Well, of these four graphs on page 3, 4, which are direct variation? Well, we can see here, here's direct variation because we're starting 0, 0. 0 hours of a rental of the batting cage costs $0. We're starting 0, 0. Also, Sally, this is a direct variation graph because 0 games played, she has 0 points. So that graph starts at the vertex 0, 0 as well. We can see on the other graphs, page 4, we're not going through the 0, 0 vertex, so they aren't direct. So we're looking at the two graphs on page 3 and 4 for this. So what do we want to do with those? Well, in this case, what we're looking to do is, I didn't transfer all the information onto it, but we want to basically calculate the slope for each of these. So if I were to very quickly, again, it's 0, 0, $20, 1 is 20, 2 hours would be 40, 3 is 60, 4 is 80, 0, 1 is 20, 2 is 40, 3 is 60, 4 is 80. There's our graph. But let's calculate the slope for this graph. Now remember, there's two ways to calculate slope. We can do it with a calculation, or we can do it just by counting. Slope is change in our vertical over change in our horizontal. I could do it with the calculation by picking 2 points. Any of these points, it doesn't matter which 2 points I choose to use in my calculation. Any two, because they're in a line, will work out to give me the same slope. So look at, here they are here too. There's our 240 points and there's a 480. So those are the 2 points I'm going to focus on. 240 and 480. Well, how do I calculate slope? Change in y's. I'm going to go my y's, 80 minus 40, over change in my x's, same order, 4 minus 2. So we end up with 80 minus 40 is 40, 4 minus 2 is 2. So we have a slope of 40 over 2. But remember, what do we always have to do with a slope? Our slope always has to be reduced, which becomes 20 over 1. Now here's what's interesting about slope of a graph in a word problem situation. What are the units for our y-axis? Well, when we look at the y-axis, we're talking about cost. So this is saying a cost of $20. And what is our x-axis for the second calculation? Well, it's hours. So it's $20 over 1 hour. The slope isn't just some arbitrary value. The slope works out to be $20 for 1 hour. So slope works out to be the cost of the rental. That's not a coincidence. Slope is an important value for word situations. There you go. Now, very quickly, the other way to calculate slope, if you recall, is by counting on the graph. What we just have, if I use the same 2 points, I want 2 distinct points that I can read from, change in vertical. But I don't say my change in vertical is just 2 lines. I have to use the scale that's there. Every line represents 10, so our rise in this case is from 30 to 80. Sorry, that's not 30, that's 40, my bad. 40 to 80. 40 to 80 is an increase of 40. And my run, my horizontal change is how many lines? Oh, from here, 1, 2. So 40 over 2. Whether we use counting or whether we use calculation. But the key here is our slope is key information from the question. So let's try Little League Sally. Again, 0 games, 0 points, 8 points per game, that's 16, that's 32, that's 48, that's 64. So this one, it's a little bit harder when we did this to read the information because 0, 0, and then we had 2, 16. So we were just kind of eyeballing where this went. It wasn't perfect, which makes it a little bit harder when we want to now use the information in a question. But we still have, 6 is 48. Which one's wrong here? 40 is 32. Whoops. 40 should be up a little bit, sorry. 4 games, 32 points. 6 games, 48 points. And 8 games, 64 points. So again, I want to calculate slope. But it's hard, if I were just reading points off the graph, they're not at a nice point where it's easy to know, oh, that's a certain XY value. But I have the information over here. So I'm going to, again, pick 2 points from there. I'm going to, let's say, use the 648 and the 432. So those 2 points are what I'm going to use. Now I can't count on the graph because I don't know exactly what my rise and run is. But I can calculate slope saying, what do we have? Slope is change in Y over change in X. So the change in our Y's would be 48 minus 32. And the change in my X would be 6 minus 4. Well, 48 minus 32 is 16. 6 minus 4 is 2. But again, let's consider what the 16 and the 2 represent. Our y-axis is points. So that's 16 points every. Our x-axis is games played. 16 points every 2 games. But we can reduce that. 16 over 2 becomes 8 points every 1 game. So again, this slope value is equal to the points per game. And if we look at the formulas for each of these when we did these, it had the cost to rent was 20 H, $20 per hour. Our slope was in the formula. For Sally, Sally was getting so many points, 8 points for every game. That was the equation we came up with. But look at this, 8 points per game. There's the slope again. So slope and word problems have very important relations. So, slope is an important value when we get to word problem situations. So if we take a look at page 12, what information can we get from this? Well, all direct variation relations have an equation of the form. Both of our equations was our y ended up being what we now know is slope times the x value. Because we had number of hours rented and there was a cost. Our y cost equaled, which we just proved was the slope times however many hours we rented. Y equals mx. Little Sally, what did we have when we graphed? Well, our x was the number of games she played, resulted in the number of points she scored. And our formula was the points she scored, y, equaled the slope, which we just showed, times the games played, which was the x. So y equals mx, where m is the slope. So all direct variation relations have a slope value that represents, and this is the key part, it represents the change occurring in the question. Yeah, because the cost, our slope, we worked out to be 20. And that was the cost to rent per hour. So the consistent cost was $20. Our slope was 20. So the slope value on your graph represents the change that's occurring in the question. They go together. Little Sally, slope was 8, and that was 8 points per game. So the slope value represented the change occurring in the question, 8 points per game. They tie together. So the rate of change in a direct variation is equal to the slope. And that we're going to keep building on and using that information. So, direct variation, a quick investigation here. You have on page 13, private dinners. You've taken some friends out and they say they're going to cost, one cost will be 20 N and a second cost would be 30 N, where C is the cost of the dinner and N is the number of guests that are attending. So that's important. So what I want you to do is complete each table of values and then graph the information. Let's see what you come up with. Give it a try. So you're going to graph. If there's no guess, what's the cost? 0. One guess, the cost will be 20. So come up with the table of values. You can then create ordered pairs, and I want you to graph that on the graph that's there. If you went somewhere and the cost was 30 N, 0 guests, well, that would be 30 times 0, $0. One guest would be $30. 2 guests would be $60. And now we have ordered pairs that we can graph on the same graph as the 20 N one. Let's see what we end up with when we do that. Give it a try. When you're finished, start the video and we'll look at it together. So hopefully you have a graph that looks something like that. We have one graph. Remember, I did C equals 20N in red and C equals 30N in green, because 3 guests would be $90 and so on. So what I want you to do is calculate the slope of each line. So for the 20N, if I want slope, well, pick 2 points. Any 2 points that you want on that graph. I'm going to use 360 and 6,120. Well, calculate slope, change in y's, 120 minus 60, over change in x's, 6 minus 3. Leaves us with 60 over 3, which I can reduce both of those by 3, which is 20 over 1. What did our y values represent? Cost. X was people. So I know cost is $20 for one person. The slope we get represents the fact that it's $20 per person for the question. Not a coincidence. Calculate the slope for the other line, for the 30n formula. Well, let's use the point here. We're going to use 260. And let's use here 150. Pick 2 points. Calculate slope. Y, 150 minus 60 over x's, 5 minus 2. What do we get? 90 over 3. Reduce that by 3 is 30 over 1. And again, our y was cost over x, which was people. So this is cost of $30 over one person. $30 a person. Your slope has an important bit of information with it. So, are these graphs linear? Absolutely they're linear. They're straight. Yes, and we would see that because there's a common change in our table of values as well. Are these different or similar? They're different, and that the steepness is different because they have different slopes. But they're similar because they're both linear. So just out of curiosity then, what would happen if we wanted to graph and it was $15 a person? Well, if it was 15 a person without doing actual data, 30 was steep, 20 was less steep, so 15 would be a line that was less. I'm not saying that those are the right values, but we know that it would follow, it would just be less steep. This information all ties together. So, and the 20 and 30, they represent the cost of the meal, which also is the slope of your graph. The slope of a graph represents the change occurring. So on page 14, here's some graphs. Determine the cost per person. Same kind of idea as the last ones. We have cost over number of people. Well, the first thing we need is slope. So I need to find 2 points on that graph that are easy to see that they're distinct. Well, if I look along this graph, I like this point here. That's 220. I think that's a pretty good point I could use. Oh, and I just happened to look up, and there's another nice point that's distinct, and it's 8 to 80. That's the point. So we calculate slope. Change in y's, 80 minus 20, over change in x's, 8 minus 2, gives us 60 over 6. Reduce that, 10 over 1, y is cost, x is people, so $10 for one person. So could we come up with an equation? Sure. Our y, cost, is slope, $10 per person. Direct variation. There you go. Now we look at the second one here. Same idea. I want you to give this one a try on your own. See what you come up with. Can you get an equation for this linear equation? Pause the video. Give it a try. All right, first things first. You need to calculate, or not calculate, but find a distinct point where it's easy to see, like here, 4 and 70. That's a nice point we can see on that graph, I know for sure it's passing those intersection points. So we have 470 as one point we could use, and we need a second point. I like this one up here. I think that 8,140 is another good distinction point. So we need to calculate slope. Change in y, 140 minus 70 over change in x, 8 minus 4. What does that give us? 70 over 4. Well, this one, can we reduce it? We can. And I'll be honest with you, let's cheat a little bit. We want to know the price per one person. So let's reduce by 4 so that we have one person for x, and that means my 70 divided by 4, that works out to be 1750. So what does that tell us? Y is money, x is people, so this is telling us it's 1750 per person for whatever it is. So what would our equation be? Our y, because remember, direct variation is y equals mx. Y cost equals 1750 times the number of people, which we're not sure of. It changes, so there's our equation. All because we know the slope. That's what's important. So another question, what if the cost for 8 people was $96? How could we come up with an equation for that? Well, our equation requires to know the slope, which is the change for one person. So if I took my $96 and divided by 8 people, we would know that that's $12 for one person. Well, that $12 per person, again, that's the change that's occurring. So that's our slope value as well. So the cost would be $12 times P. Because the change per person, the rate of change is 12, it could go into our equation. So direct variation situations. What's key to remember? Always goes through the origin, direct variation. And the slope value. That slope value is part of your equation. Your slope value is part of the equation. The two tie together. Now, with that being said, let's then look at partial variation. It's the same thing with a twist. Same basic idea we're looking at. But with partial variation, we don't pass through the origin. Partial variation says we're starting somewhere on the y-axis and then traveling for our graph. It could be that point in all kinds of different angles, or it could be starting at a different point other than the origin and going at certain angles. But the whole point to partial variation is it doesn't start on the y or on the origin. We're starting on the y-axis. So let's do the same thing we did before. Let's go to page 3 or 4. Which of those graphs are partial variations? Let's again calculate slopes. The partial variation, let's now identify the y-intercept. Where does it hit the y-axis? And let's take a look at that information. So if we go back to what we did before, we had these first two. We identified that these were direct variations, so we don't even worry about those. But now we can see we have partial variation because both of these graphs don't start at the origin, but they're starting somewhere on the y-axis. And that's important. So let's see what we can get with this information. On page 3 and 4, again, I haven't filled in all the data from it, so bear with me. I got to quickly put that in, and then we'll keep going. Okay, so our equation for bowling, if you recall, the cost to bowl was going to be $15 plus $10 per game. Well, let's calculate the slope of this graph. What do we have to do? We have to pick 2 points. Any 2 points you want, whichever works for you. I'm going to use 120 and I'm going to use 455. So slope will be change in my y's, 55 minus 20 over 4 minus 1. When we do that, 55 minus 20 is 35. Am I doing this right? 1 is 25, not 20. My bad. So sorry. Another small error. 55 minus 25 is 30. 4 minus 1 is 3. We can reduce that to 10 over 1. Our y is cost. Our x is games. $10 per 1 game. Why is that $10 per 1 game so important? Look at that. It's part of our equation. The change that's occurring, $10 per game. But the second thing we were going to look for was where is our y-intercept? We hit the y-axis at 15. So our y-intercept, where we're on the y-axis, is 15. Well, is that just some value? No. It's the starting amount for that question. The cost is $15 to start, which is our y-intercept, plus $10 our slope, because that's the consistent change for our x value. So these formulas aren't just a coincidence. Everything ties together. So again, very quickly with the second one, our repairman, if you recall, the equation was the cost to bring in the repairman was $50 up front plus $25 for every hour worked. Well, if we calculate the slope on the graph, pick 2 points. I'm going to use 2 100 and I'm going to use 6 200. Well, slope is change in y's over change in x's. We get 100 over 4, and when we reduce that, it becomes 25 over 1. Y is dollars, X is hours, $25 per hour is our slope, which is also part of our graph, our equation, sorry. And the second part to that, what's the y-intercept? We see that we hit the y-axis. The y-intercept is at 50. That 50 is also part of our equation. We started at $50 no matter what. There's our y-intercept. We were charged $25. The consistent change was $25 for every hour. That's our slope. All of this information ties together. And that's where we come up with the partial variation equation, y equals mx plus b. This is what everything hinges upon as we move forward in this unit. Y is our resultant value, but the key is slope. What does the slope represent? It's the rate of change. It's the consistent change for the question. Being charged $25 per hour. That's our consistent change. And B, that's our y-intercept, which is the starting point of the question. Because we don't start at 0. We started at $50 just to show up for the repairman. That was our B value. The other one, we started at $15 to rent the lane before we even played. That was our B value. All of this information ties together. So I want to write an equation for each situation. So let's take a look. It says the cost of a banquet is $30 per person and a $2 rental fee. Well, if I want to come up with an equation, we're thinking y equals mx plus b. Well, I always like to start with b. What's the starting value in this that only happens once? It's a $200 cost. You pay the $200 cost once and once only. But what else do we have? The slope, which is the rate of change. We know we're being charged $30 per person. That's the consistent change over and over. So slope is 30. Starting point, change that's occurring. So now I can create my equation, y equals, well, now I can put my slope in. 30 times x, which is the number of people. When I look at my table of values, x is the number of people and y is the cost. So I could even make this equation a little better. Instead of saying it's y, our y in this case is the cost of the banquet, which is slope $30 for every person x. But we also have to pay that initial amount, which is $200. So there's the equation for this situation. Cost is 30p plus 200. For B, you're going skiing. There's a 30 centimeter base of snow at the hill. They have 30 centimeters already on the ground. And they're getting snow 4 centimeters per hour. So what do we want to know? Well, we need to know what's the B value. What are we starting with? We're starting with a 30 centimeter base. It's already there. But what's the slope? What's the change that's occurring? 4 centimeters per hour. So now I can create my equation. How much snow is there? Well, X is the hours of snow, but my resultant Y is the amount of snow. So, sorry, that's my Y's. So what does Y represent? The amount of snow on the ground is going to be mx, slope, times x, which is the number of hours. 4 centimeters times however many hours it snows for. But now we add the B value, which is what we started with, which was 30. And there's our equation. So we can create equations that tie into the graph, because now with those equations, we can do a graph. I'm just going to rewrite them so I can see them better. C equals 30p plus 200, and the amount of snow equals 4h plus 30. Well, there's different ways to do this. I could do a table of values, but at the same time, well, part of it is, what do I know about this equation? I know that my B value is 200. So I'm going to start at 200. I also know that my slope is $30 for one person. Well, if it's $30 for one person, we can see that our scale here goes up by 5s. So let's actually say that what's the cost for 5 people? Let's take our slope and make a bit of a change. If it's 30 for one, 5 people would be 150. So if I'm starting at my B value, I know that as I go change in Y, I need to go up 150 to 350, and I need to go over 5. There's my next point. 5 people would cost 350. How would I get to the next point? Well, use the slope. I need to go up another 150 to 500. Go up to 500, but I need another 5 people, so I'm going to go over to 10 people. So I can move my slope. Rise of 150, run of 5. Rise of 150, run of 5. And I'm not moving by lines, I'm moving according to the scale. Rise of 150, run of 5. And I can create the graph. Because the equation gives me my starting point, my y-intercept, and the slope I need to move, but I can convert a slope to be helpful for me. So let's try this one. Slope, or amount of snow is 4 hours, 4 centimeters per hour, but there's a base of 30. So our B value is 30. We know we're starting at 30 centimeters. And we know our slope is 4 centimeters every 1 hour. There's our slope. So I could move 4 centimeters up. My rise could be 4 for every 1 hour. But we can see here that our x's are going up by 2's. So let's change the slope a bit. Instead of 4 over 1, it would be 8 over 2. Same values, but now our rise of 8, I need to go from 30 up to 38 in 2 hours. There it is. What's next? I need to go up another 8. Well, and it's hard if it's not marked to do that. But rise of 8, well, that would be from 38 to about 46. So up to 46, but a run of 2. And there we go. And we can keep doing that movement. Rise of 8, run of 2. There's the next point. And we end up with these points forming a linear graph. Because our equations give us a B value to start with and a slope to move. So that is how these things tie together. Page 16, we have a taxi company. Charges a $5 fixed fee and $2 per kilometer. So, what's the initial value? $5. What's the rate of change? $2 every kilometer. That's the consistent change. So what's our equation? Y equals mx plus b. Y equals m, which is our rate of change slope, times x, plus our initial value, which is our b value. There's the equation. Let's put different variables in. What are we solving for? The cost of a taxi, which is 2 for every x, which is kilometer driven. 2 times every kilometer plus $5 gets us the cost of a taxi. We could create a table of values from that now that we have information. I'm not worried about the table of values quite so much. What's our x value? Our x value is kilometers. Our y value is the cost. So we could put in 0 kilometers, 1, 2, 3, 4, 5, and so on, and fill it in. This can help us. So what's the total cost of a 20-kilometer ride? Well, what's great is we have an equation for that. The cost is 2 times kilometers plus the $5 fee. We want to know the cost for 20-kilometer ride. Everything ties together here. We get a $45 cost for a 20-kilometer ride. All of these pieces fit together. So from there, actually don't worry about that. Let's go, actually right now, supplemental pages 36 to 38, 36, 37, 38. They're thinkers. Give them a try. Read the instructions. Consider all the time y equals mx plus b. Well, on a graph, b is where we are on the y-axis. Slope is the calculation. Change in y over change in x. But in a word problem, b is an initial value, and slope is the change that's occurring, the rate of change. Three very distinctly different ways of identifying the same information, tying it all together. 36, 37, 38. Give it a try. Reach out if you're having troubles. But most important, have fun.